From question number 5, I am selecting one problem that is say the problem G, and in this problem G, the vector has been chosen from, if you can recall, it has been chosen from the set M2 cross 2R. Try to identify these notations that these things have already been discussed. Okay. And the span set, the set capital S has been chosen as 1, -1, 0, 0, and 0, 0, 1, 1, and 1, 1, 0, 0. Okay. And you see that I have to check whether this can be expressed as span of S or not. So let us select scalar quantities A. Let me write it properly. Okay, so I'm going to express this vector as a linear combination of these vectors. I'm going to check whether it is possible or not. Okay, and this A, B, C are real numbers. So we can write it in the following manner. And this can be written as A plus C and B plus C and minus A and B. And if I equate the term cell wise, then we get A plus C is equal to 1, B plus C is equal to 2, minus A equal to minus 3, that is A equal to 3, B equals to 4. Someone has written something in the chat box. So two people, Priyangshu Gui and 1108, they have got the same result. But I can see a little bit difference between your results. Someone has got, Priyangshu has got C equal to minus 2, and 1108, he has got C equal to 2. Yeah, probably printing mistake is there. Nikita Singh and Shubhadeep has got C equal to minus 2. Okay, so actually you have got the point. So, and whatever problem I have selected from here, I'm choosing arbitrarily, but all of these vectors are actually, getting, we are able to express each of these selected examples where vectors have been expressed as linear combination of other two vectors. But remember, this should not, probably this is not the case for all the examples. So you have to check all the examples individually. And there is a problem in the book, which I'm writing over here, question number 10. This problem, you remember this, try to do it and remember the result also. Show that if M1 is equal to 1, 0, 0, 0, and M2 is equal to 0, 0, 1, 0, and M3 is equal to 0, 1, 1, 0, then span of S find it out. What is span of S? Do it by yourself and tell me what is it. What will be the span of S? So select your scalar quantities 1, 0, 0, 0, and B 0, 0, 0, 1, and C 0, 1, 1, 0. And if I do the simplification, let us see what we are getting. if I add these numbers, A plus 0 plus 0, 0 plus 0 plus C, that is 0 plus 0 plus C, and that is B. Now, let us name this matrix as capital A. Let us take the transpose of A. If I take the transpose of this matrix, what we get? We get AC and CB, which is same. And therefore, A is a symmetric matrix. A is a symmetric matrix. This A, B, C can be any real number. This A, B, C can be any real number, and symmetric 2 by 2 symmetric matrix is also the member of M2 cross 2R. It is also the member of M2 cross 2R. Okay, so it is a symmetric matrix. This result is very important because you have to remember these generators. So actually, the important part of this particular problem is remember that this type of matrices, this set of matrices generates all symmetric matrices. If you sit for GATE examination to study MTech, this topic of vector space is all very important. And in one of the question paper, once I have seen that this question was asked in GATE. GATE is examination is an MCQ type of examination, you know. So they gave options over there, and they asked which of the following set defines a symmetric matrix or generates a symmetric matrix. So this example is very important. So therefore, star mark for this. Okay. You are going to encounter linear algebra problem in GATE examination also. Next is, and question is, what is the generator of all 2 by 2 matrices defined on a field? What is the generator of all 2 by 2 matrices defined on a field? It is given in question number 9. So I'm just writing the answer. So you have to remember this result also. If you want to sit for GATE examination. So answer is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. That is the generator of all 2 by 2 matrices defined on a field. Okay. So you have to remember this set also. And this is very easy to remember. Suppose you see the element 1, actually if you think that it's very difficult to remember, you see the movement of 1. Okay. Actually, it would be nice if I could have written this first and that. If I can write this first and then this one. See, you see, 1 is present in the 1, 1 cell. Then in the next, it has come to 1, 2 cell. In the next, it has come to 1, 3 cell. 2, 3. Clockwise rotation. 2, 2 cell, and then it has come to 2, 1 cell. Okay, so a clockwise movement is over there. Okay, so you can remember this generator very easily. You can also think of the generator of skew symmetric matrix. It is not given over here. Try to find it out by yourself. Yesterday, I made a very important discussion on skew symmetric matrix. Okay, so it's in this particular set of example. So in this particular, when you study something, you study it carefully. As in this particular exercise, they have given us the generator of any 2 by 2 matrices. They have given us generator of any symmetric matrices. Why didn't they give us generator of skew symmetric matrix, you have to think. I also have to think why it's absent from here. Probably in our yesterday's discussion may help in this regard. We have to look for it. And there is a Dagger problem, you see. The problem says that prove that, what is the problem? Span of this set is equal to AX, where A belonging to F. Okay, for any vector X in a vector space, interpret the result geometrically. Interpret the result geometrically. In R3. Interpret the result geometrically in R3. Okay. So if you want to prove it, the dagger signifies, the dagger of the problem actually signifies that, as I told you in the previous example, a few minutes ago, in the previous session, that dagger means this particular result is very important in the sense that the result, do not treat this as a problem, treat this as a result. And this result has actually been, used somewhere in the later chapters. That we cannot, probably you are not able to understand right now, but you are going to get its application maybe in some solved example or maybe in some exercise in the subsequent chapters. So this example is also actually very important and we have to solve it. Okay, we have to understand this particular problem. That is the first thing which I need to say to you. Secondly is that when we want to, suppose capital A and capital B are two sets, okay? They are two sets. So if we want to show that capital A is equal to B, we need to prove that A is a subset of B and at the same time B is a subset of A. A is a subset of B. How to prove it? Take an element from A and show that X belongs to B. How to prove B subset of A? Take another element from B and show this belongs to A. If you can show it, then it implies that together they imply that A equals to B. That is the rule. That is the rule of set theory, which I'm going to apply over here. So my first set A is capital A. My second set is capital B. Okay. So let us try to prove it. Proof. Let us name let us name this element as, what should I say, E. Let E be, E stands for element. Let E belong to span of S. Okay. Let E belongs to span of S. Now, since X contains a single vector, a single point, single element, X contains a single element, then as E belongs to span of S, the span of X, this implies E can be expressed as linear combination of vector in singleton X. This implies there exists a scalar A belonging to F for which E is written as A into X. E is written as A into X by definition of span. And this implies that E can be treated as a member of the set. E can be treated as a member of the set AX such that A belonging to F. Therefore, E belongs to span X implies E belongs to this, and therefore span of X is a subset of AX, A belonging to F. Here actually I'm writing, the problem may look very simple, but here actually I'm trying to say to you that how to write a proof. I have never discussed it in the class. So that is one case, case one. Case two is that let us consider any other element E prime from the set AX such that A belonging to F. Okay, so this implies that there exists a scalar, say A prime belonging to capital F such that E prime can be written as linear combination of X. So, try to see how I am taking the notations to express what I need to express. Okay, so A is any general scalar. So if E prime is any special element of any particular element of this particular set, so I am considering for this particular element E prime, I am considering a particular scalar present in F so that E prime can be expressed as this, because E prime is a member of this. Now, since X is the only vector, only element, shouldn't write vector actually. Or I can write vector also, only vector. It would be nice if I write it. Since X is the only vector present in singleton X, and as E prime has been expressed as linear combination of X, so E belongs to span of E prime belongs to span of X. And this implies that since we have started with this, E prime belongs to this, now we have got E prime belong to span of X. So AX, A belonging to F, is a subset of span of X. Okay, and we can consider this to be number 2. From 1 and 2, span X is a subset of this. This is a subset of span X, and therefore span of X is equal to AX, A belonging to F. Proved. So that is how you have to write the proof. Remember this result. Whenever you are talking about two sets and we want to show that the two sets are same, then we have to use this set theory result. Remember, to prove something, I have often seen that to prove something, when I ask students to prove something, they use special example. They show the proof by an example. That should not be the case. Examples cannot generalize your proof. Proof should be general. Examples are special case. You cannot, to prove something, you cannot take the help of the example. Remember this, this suggestion of mine. Okay, always. Now, later comes the geometrical interpretation. Geometrical interpretation in R3. Okay, let us try to think it. What can be the geometrical interpretation in R3? What was my set? My set was, my capital S was X. And if capital S is a subset of R3, then the element of S is actually of the type, is a triplet. It is of the type X is a vector, na? So X, Y, Z. Only one vector is there. Now, okay. If I'm wrong, then you can make me correct. So S is the set containing a vector X. I am considering, according to this problem, I am considering here in this particular problem, in the proof, my S was a subset of any vector space V. Now I am considering the vector space V. I am considering the vector space V as R3 now, as it is given. Okay. And if I am considering S, and we know that S is a subset of R3, so the member of S, this vector, will be ordered triplet of this form. Or you can say in more general way that it is containing the vector XYZ, where X, Y, Z, these numbers are actually real numbers. Okay. Now, what is this set now? AX, X belonging to F, sorry, A belonging to F. What is this set? This set, we have already shown that this set is actually span of X. We have already proved it. So with respect to this special case, this is the span of this point, okay, the triplet. And what is this? AX. So if I write this span, simply write it as span, considered span of, this is a singletons. This particular S contains a single vector only. Remember, singleton set. Do not consider, I shouldn't write it as X, Y, Z belonging to R. It's a singleton set, remember. Singleton set. I'm not considering all possible points present in S. Okay. If I consider all possible points present in S, then S will become exactly equal to R3. So we will get vector space. So actually I'm considering a singleton set here. It would be nice if you write it in this manner, X1, Y1, Z1, especially. So actually I am going to write the span of this particular set S. And S, according to the problem, it is nothing but, this set is nothing but A, X1, Y1, Z1, where A is a real number. And that is your span of S. And therefore your span S becomes, span S is actually becoming AX1, AY1, AZ1. So it implies, it geometrically represents that your vector, the vector is getting the vector x1, y1, z1 is getting elongated if a greater than 0, getting contracted if a less than 0, and if a is equal to 0, then this represents the point origin. Okay. So span of S is actually the span of S, depending upon the characteristic of this particular scale. I'm back. I have not left. Sorry for the interruption. Suddenly something has happened, and that due to network trouble, I have lost my board work. Okay, you are going to get it in the YouTube. No, don't worry. So actually I have shown that. Okay, so actually I'm going to show if you are not able to copy the problem, the solution in your copy, then don't worry, I'm going to upload this in the YouTube, and then you are going to see it. So just before the disconnection, I was talking that I was getting the vector, I didn't write it correctly. I was getting the vector as this one, as this, as of this form. Okay, and this particular portion, have you got it? I mean, I was talking that I showed span of singleton X to be this particular set, and for R3 we are considering the singleton vector as x1, y1, z1. And in this case, if I try to imagine what this vector signifies with respect to this, what does it signify geometrically? That was the question. So it signifies this point. It signifies this point. A is the scalar quantity which can be positive, which can be 0, or which is equal to 0. Now, depending upon the nature of A, depending upon the nature of A, this span of X, span of this will give you 3 cases. One, the vector x1, y1, z1 is getting elongated for a greater than 0. The vector x1, y1, z1 is getting contracted for a less than 0. The vector is origin, represents origin for a equal to 0. So this is the geometrical interpretation of the problem which I have done just now. This is the geometrical interpretation. interpretation. Okay. So I have actually solved problem number 11 for you, and I have given the geometrical interpretation also, and this is also a very important problem with respect to gate. Okay, these questions are very important and very beautiful problems are they with respect to, they have asked you to geometrically interpret what does this mean with respect to R3. You could be asked this problem with respect to R2 or anything else. You could be asked this problem with respect to matrix also. Okay, so anyways, so other results which are given in question number 12, 13, 14, 15, 16, 17 in the book, these results are also, I'm actually stopping the share of this whiteboard and I'm going back to the PDF file so that you can understand, I can properly say what I actually want to say to you, that other problems 12, 13, 14, these problems, if you have time, then you can, try this problem by yourself. You can show that these two things are, these problems can be proved. Okay, say for example, show that the subset W of a vector space V is a subspace of V, if and only if span of W equal to W. This result is very important. If you have a subspace, then you want to, and if I ask, if you have a non-empty set, and if I ask you that this set, this non-empty set is a subspace of vector space V, then what do? We actually check the three properties, that the zero, it contains the zero vector, it contains, if two vectors are present in the set xy, then x plus y is also present in the set. And if x is present in S and the scalar quantity is there, then their product is also present in S. So if you know this result, then you don't have to use all these properties. You can use this as a theorem, that if you can show that W is there, and if span of this W becomes the W itself, if a non-empty subset or a vector space is there, and if you can show that the span of this set is the set itself, then you can declare that the W is a subspace of. Okay, so this result is very important. And similarly, other results also. Okay, the union of two span sets can be, span of union of two sets is actually the linear sum of the span of the individual sets. So all these results, if you can prove, or otherwise you can write down it somewhere in your copy so that you can memorize it, you can remember it, and you can later use it when required. Okay, so this chapter is very important in this regard. And then there comes this particular topic, linear dependence and linear independence. Okay, so after this linear independence and linear dependence, this topic has there which I need to discuss next. Now you see, let us go back to the syllabus part. In syllabus, you see what is written: linear dependence of vectors in this particular module. Linear dependence of vector is there. Okay, so actually now I am shifted. Gap has been fulfilled. All the gaps have been fulfilled. And now after vector space, we have studied subspace. Then we have studied linear combination of vectors. Then we have studied spanning set. And then after this, we have come to this part, linear dependence of vectors. I don't understand why they have mentioned only linear dependence, because linear dependence and linear independence, they are complementary to one another. And then in this section matrices, they have written a linear independence. So this thing, this linear independence and that linear dependence, these things are actually not separate from one another. These things are same. I mean, they are connected to one another. This is, so you don't consider module 3 as a separate module. It is a part of module 3, is actually a special case of module 4. Okay, so in the next session, in the next class, we are going to discuss about linear dependence and linear independence of the vectors. In the next class means, I don't know what will I discuss with CSE section B next, because if I get a class with CSE section A, in this week, then I'm going to discuss this part, this linear dependence and linear independence with them. And I shall upload the video in the YouTube. So CSE B are going to get next to next topic of that. Okay. But if I do not get chance of discussing this thing with CSE section A, probably I will not get chance because I do not have any class with CSE section A in this week. So in CSE section B, I'm going to meet with CSE section B in on Thursday, 31st in the morning, 9:30. So 31st night is important for you. 31st morning is not important because this is the last day you see, and the last day of your in this beautiful year of 2020. If you don't learn, don't attend mathematics class, then we'll be sorry for that, all of us, because sorry, so beautiful year it is. We are, isn't it? So therefore, 31st morning we can do mathematics. 31st night we can celebrate. We can kick 2020 out of our life. So we are going to meet on Thursday, 9:30 in the morning, and we are going to discuss this linear independence and dependence over there. Okay. So I hope by then we'll be able to solve lots of other problems discussed so far in the chapter of vector space and the vector subspace and linear combination spanning set. Whatever you like, you can choose and you can start solving the problems. Okay. So this much for today. I hope I am able to communicate the I'm able to make you understand the topic of discussion today. And I think that you'll be, maybe there are some doubts in somebody's mind, but if you study, if you read the book, because since the book is given to you and I have given you a specific book, see, you can select, you can choose, and the college has provided another book, Kryzek, Advanced Engineering. College has provided a book for Advanced Engineering Mathematics Kryzek. From there you can select problem from the chapter of linear algebra, but you study linear algebra from Friedberg. And since we are, both of us are actually, you and me are actually connected with this common connection is there, this Friedberg. I have this book, you have this book with you. So we can communicate with one another in a beautiful way. And therefore, if you study this book, if you study Friedberg, that will be much helpful, not only in engineering course, but also if you are sitting for any competitive examination later, then this knowledge of linear algebra will be very much helpful. In engineering subjects also, like deep learning and neural network, you are going to get tremendous amount of applications of this topic. So read this topic seriously, in a serious note. Don't neglect linear algebra. With this, I'm going to end my today's session. We are going to meet on Thursday at 9:30 in the morning. Till then, bye.